In this lecture, we'll talk about high-order scheme, extrapolation, and deferred correction for negative eta prime is equal to f. So for the high-order scheme, again here we're solving negative eta prime of x is equal to f of x, given the boundary condition u0 is alpha, u1 is beta. First of all, we're going to use, for example, the method of undetermined coefficients. Or the Vandermonde matrix to obtain a scheme. High-order scheme. This is, as we mentioned, this is coded up in the book by the subroutine called FD COE FFV, something like that. Also a wider stencil for higher order. For example, instead of the -1 to -1 on xi minus 1, xi plus 1, we can do a 1, -4, 6, -4, 1 on xi minus 2, xi minus 1, xi plus 1 to xi plus 2. So the procedure is basically the same as the -1 to -1 scheme. The only difference, of course, the matrix is different. Instead of 3 diagonals, we're going to have 5 diagonals. But the only real difference is that at x1, okay, remember we have 0, 1. We start from x0 and then x1, right? Here is xm plus 1. Here is xm. So we need to enforce the equation at x1 to xm. At x1, we need, because now we need more than 1 point on the left. For -1 to -1, we only need 1 point on the left, which is x0, but now we need 2 points. So we need a point to the left of x0, which is, we write that as x minus 1, x0, x1, x2, x3. The tricky part is, what about that x minus 1? Similarly, at xm, we need 2 points on the left, which is xm minus 2, xm minus 1, xm plus 1, xm plus 2, right? So we have, again, one more point outside of the domain. What do we do? One solution is that use a different white stencil at x1 and xm. For example, at x1, instead of the symmetric 2 points to the left, 2 points to the right scheme, you can do x0, x1, x2, x3, x4. Okay? And at xm, we can keep xm minus 3, xm minus 2, xm minus 1, xm plus 1. So it's the two endpoints, not the two endpoints of the domain, but the two endpoints of where we need to solve for the u. We would have to use a asymmetric stencil. For those, you can again call the FD, call if V to figure out the scheme. The next topic is the so-called extrapolation. The idea is that for the U double prime is equal to F equation, and if we have a scheme, if we have a grid, which we are going to use, here is x0, here is xm plus 1, and the mesh size is h, okay, and for another grid, if the mesh size is h over 2, in other words, we have doubled the number of intervals, alright, e.g. here, if you have 10 intervals, and here is 20 intervals, right? So for 10 intervals, m is actually 9, and here m is actually 19, okay? So it's like here we have an extra point here, okay? For that case, and for this particular equation, we have the following, as we did the error analysis, the u minus uh. This is for the -1 to -1 scheme, okay, is order 2. So this is actually equal to c2h squared plus c4h to the 4th, and so on and so forth, okay? And if we denote, so we denote the solution for the first grid by u sub h, and here the solution by u sub h over 2, just to differentiate the two different approximations on two different grids. So for the second solution, the error is c2 times h squared, but this h becomes h over 2, okay, squared, plus c4h over 2 to the 4th, and so on and so forth. For this particular simple equation, negative u double prime is equal to f, the two c2s are the same, if they are the same, and we need to think about why that's the same for this equation. Now, assume we showed that they are the same, then the question becomes, can we find a constant a such that if we define UH star, which is a convex combination of the two, a UH plus 1 minus a UH over 2. Then we have the new arrow with the two guys put it together is of order a to the fourth. Okay. So the answer is actually yes. If you look at the arrow, right, the U minus UH star, okay, this we know, of course, this given the assumption of UH star, this is a UH plus 1 minus a UH over 2, okay, and for U is AU plus 1 minus AU, of course, minus, if you rewrite this, AUH plus 1 minus a UH over 2. This is just, we put the two guys with a together, that's a times U minus UH, plus the coefficient 1 minus a, that's 1 minus a U minus UH over 2, okay. So what does this tell us is that this is a, we know U minus UH is C2H squared plus C4H to the fourth, so on and so forth, plus 1 minus a times C2H squared over 4 plus C4H to the fourth over 16, right, and so on and so forth. So if we combine the h squared term, we're going to get C2 times a plus 1 minus a divided by 4 h squared plus what the order h to the fourth. Okay. The question then becomes, can the linear combination be more accurate? The question is, can we make this 0? The answer is yes, if you set a to be negative 1 over 3, right? That's a minus a over 4, that's 3a over 4 plus 1 over 4 is equal to 0, okay? So the idea here is that you solve negative eta prime is equal to f using second order accurate scheme twice, right? Of course, the twice is on different meshes. To obtain, if you solve this twice and to obtain, and you're smart, you can put the appropriate linear combinations together. You can obtain a fourth order accurate approximation. This is actually very nice. If you think about it, the idea is that if the h is 0.1, okay, 0.1, and a second order scheme, this would be like you have 0.01 error, all right. If you get a fourth order scheme, that's 0.0001. And if you want that error, the h here is like 0.01. Alright? So we should change this to capital H, and capital H, and then have small h. That means if you need the error, so which means two ways to obtain an approximation with the error at the 0.0001 level. Alright? One is that you use the second order scheme then if you use the second order scheme once, you would need a mesh of size 0.01. Okay? Or you use also the second order scheme once on a mesh of 0.1 and once on a mesh half of that of 0.05, and then combining them, you would also get an accuracy of 0.0001. And note, the method 2 is much cheaper. I mean, not necessarily a lot cheaper for our example, our numbers. If you raise that's 0.0001, it's just one example. If you put that as 10 to the negative 16, for example, then there will be the size of the matrices will be very different. So it's a matrix of size. If you do 0.01, you will need m to be 99. Okay, 99. So m is 99, m plus 1 is 100. Then you get the mesh size 0.01. This versus matrices of size m equal to 4.1, you only need 9, and another one 0.005, that's 20, that's 19, right? You solve two smaller matrices, you get the same error, and you are smart in combining the two solutions. You get the error as if you were solving a matrix of size 99. That's a pretty good deal. The last topic of this lecture is so-called deferred correction. Here we go back to the local truncation error analysis. Remember when we did the local truncation error analysis, we have AHE is tau. The AH is a 1 of h squared to -1, -1, -1, -1 matrix. Okay. So the error is EU minus UH. Remember, or let's write this again. The tau I is that the i's, you plug in the exact solution, into the scheme, you have negative u xi plus 1 plus 2 u xi minus u xi minus 1, alright, minus f xi, and then we expand uxi plus 1 and uxi minus 1 around uxi. So that gives us negative u at xi, ui, alright, plus h u prime I plus h square over 2 u double prime I plus h cubed over 6 u triple prime I, okay, and so on so forth, and plus 2 ui minus, we have ui, now the difference is minus h, ui, u prime I plus h square over 2 u double prime I minus h cubed over 6 u triple primed I, so on and so forth, divided by h squared minus fxi. Indeed, in fact, as we did before, we need to add one more term. This is going to be add h to the fourth over 24 u to the fourth derivative at I, okay, and here is add h to the fourth over 24 u to the fourth derivative at I, and we see that the order term cancel, right? ui the even, yes, the odd terms cancel, so this cancels with this, and this cancel with this. The first even term, ui, and the 2 ui cancel. So what we have left is that we have minus h squared u double prime at xi divided by h squared, okay, and then we have minus h to the fourth over 24, 2 of them over 12, u to the fourth derivative at xi, this is also divided by h squared, plus the u to the fifth cancel, we have left is order h to the sixth, and this divided by h squared as well, minus f at xi, alright. So this guy cancels with that guy because u is the exact solution. And we did this before, so this is negative h squared over 12 u to the fourth derivative at xi plus order h to the fourth. Okay. In this particular case, what we notice is that we have the equation negative u double prime is equal to f. This is at any x. From here, we can calculate the u to the fourth derivative, okay, because this is u double prime and then double prime. So this is negative f double prime, which is negative f double prime. F is given. So that means that our tau I, which is AHE, okay, is equal to this i's component is equal to tau I, which is equal to negative h squared over 12 times u to the fourth derivative of I, which is negative f double prime at xi, plus next term is order h to the fourth. Okay, which is simply h squared over 12f at xi plus order h to the fourth. What this says is that if we forget about the higher order term, so this is like AHE is kind of like h squared over 12 f double derivative. We lost the double derivative there. F double derivative evaluated the vectors. Okay. So this means we can solve for the error. We'll solve the error E. So E is our AH inverse times square h squared over 12 of f double derivative. Okay. And of course, we're not actually solve the whole error. We only solve the dominant part of the error because we only know the dominant part of tau I. So that means once you have a UH, you can update. So you have UH, and then if we solve AH inverse times h squared over 12 f double prime, alright, this vector f double prime evaluated x1, x2 all the way to xm, the vector. And once you solve that, we can update either UH, if we define UH star to be UH plus that change H inverse H squared over 12 F double prime vector. Okay. Which means if you think about it, the U minus UH star, right? This becomes U minus UH minus that AH inverse H squared over 12 F double prime. This is like we know U minus UH as we showed above, U minus UH by stability. We know that the dominant part of that, the E, okay, this is as if we are subtracting the dominant part of the error from the error. Okay, so the dominant part of this part is that part. So what's left is the higher order term, which is order h to the fourth. Okay, this guy is that guy. In fact, we don't need to solve this twice. What we had above is we first solve for UH and then solve again. There are two solves. In fact, you don't need to do that. Instead of what we have been doing, H inverse times F vector, we do H inverse times F plus that H squared over 12 F double prime, F vector, F double prime vector. Okay, this is like one solve gets us the UH star right away, right? Instead of UH AH inverse F and AH inverse that 12 H squared over 12 F double prime and then update UH, we just do one solve. So this is two linear algebra solves, and here is only one solve. So what we have here for the default correction is that by doing some analysis, we can turn a second order accurate scheme into a fourth order accurate. It's similar in flavor to the extrapolation, but the technique is different. By actually resolving the dominant part of the error and put it back into the solution, basically. So we have a more accurate post-processed solution.